Okay. Good morning, everybody. Welcome to this LAT colloquium. I'm very pleased to introduce Professor Pierre Jean. He's professor at the University of Toulouse and working in on one of the topics related to our research topic, very relevant, and it has been involved, is the origin of depositor minerals. So they have published several papers about that, at our speed, especially. Also, and this is the topic today, has been working with the, this is still working with the Fermi satellite, the NASA Fermi satellite, and in particular the Large Area Telescope is satellite. And in particular, it has been studying novae that have been detected with the satellite, not with integral, but Fermi, yes. And well, his collaboration with us, ICE, Jordi and myself, started already in 1996. Yeah. So it was in the topic of supernovae, where they have one detection, integral, and it was crucial his collaboration for the data analysis, and for the collaborators in Toulouse as well. No? And with myself and V407 Cyg at the University, the topic of novae, in the case of predictions, because we have not had any novae postdoc up to now, and integral has finished. So, then he's intelligent and he's involved now in the future instruments. In this range, and in particular in COSI, which is a NASA project. So the tools, since they know very well how to do these analyses that are very complicated in this mission, and with a lot of background knowledge, he is collaborating as the ICE way now, COSI.
Collaborator is the COSI team.
Because it's participation. And also he's involved in the Cherenkov telescope array observatory. So he's working also. Yeah. So this is very high energy gamma rays in the GeV and PV range. Well, so welcome. And
yeah. Thank you. Thank you, Margarita, and thank you for inviting me. It's true that we search for the emission, the gamma ray emission from novae, the nuclear gamma ray emission together since a lot, and actually. We did not detect anything in the MEV range, and instead we detect the JV emission with LAT Fermi. And this is what I'm going to talk to you about today. So I will start first to briefly remind you what is a nova. We have experts here, but there's two slides just to show you what is a nova, and also what is LAT Fermi. And then after that, I'm going to actually this is a kind of a summary of what I've been involved in during this since 2010. We detect the first emission of gamma ray emission from a nova with LAT Fermi, and since then I'm still working on that, searching for emission, trying to understand the origin. And this is a summary of what I've done, roughly. Oh, not all, but I try to make a review also. But Okay, so this is the first time I present that, so I'm sorry. It will be a kind of, in French, we said improvisation. Okay, so excuse me. I'm going to try to be as clear as possible. Okay, so first, okay, what is a nova? This is the first slide. So a nova is actually a thermonuclear runaway of a layer at the top of the second. Okay. Sorry. Okay, so, and in this explosion, you have the envelope that is ejected at 1,000 kilometers per second. You have the luminosity of the system that increased up to 10 to the 5 roughly the solar luminosity. And after the ejection, you have the hot white dwarf that is very hot because you have the nuclear burning at the surface. And this hot white dwarf, due to the radiation pressure, is going to produce a fast wind that is in addition of the ejecta, contributing to the physics of the event, of the nova. So this kind of event, we estimate that we have about 40 novae per year in our galaxy, but actually we detect only about 10 per year, roughly. So in optical, these are bright events, so we detect them mostly in optical. Okay, we are going to distinguish two kinds of novae. We have what we call the classical novae, which consist actually in systems with the binary in a closed orbit, here with the distance between the white dwarf and main sequence star of about a star radius. So actually the main sequence star is filling the Roche law, and so it fits in matter the accretion disk that is here around the white dwarf. So the accretion is made here via this accretion disk directly with the matter of the main sequence star. So this is a closed binary. And we have the symbiotic system. This is a symbiotic or recurrent novae, which are so a white dwarf and a red giant, mainly, with a separation that are about 100 or around 100 times the solar radius. And in this case, the accretion is mainly made by the accretion of the wind of the red giant white dwarf, of the red giant stars. Okay, so this is the presentation of what is a nova. Now, what is the LAT Fermi? So LAT actually is the large area telescope of the Fermi gamma ray space mission. You have a nice image here of this mission that has been launched in 2008 by NASA. And this mission has two main instruments, so the large area telescope and the gamma ray burst monitors. And the LAT is a very large area because it's quite large, so 1 square meter roughly. A pair conversion telescope that is shown here. And it is composed of 16 modules here that are composed of a tracker here and a calorimeter just below. And so you have this system, these modules that are embedded in an anti-coincidence system in order to reject all charged particles that arrive on the instrument that contribute to the background. Okay, so the principle is that the tracker here is made with layers of tungsten and silicon detectors. And this system of layers of tungsten and silicon detectors allows to, thanks to the tungsten, to convert the gamma ray that we want to study, the gamma ray from the source, to be converted in the electron-positron pair via the pair creation process on the tungsten. And then the electron and positron is tracked thanks to the silicon detector. So you can detect the tracking, you can do the tracking of the electron and the positron thanks to the silicon detector. So in this case, with that, it helps to determine the initial direction of the gamma ray from the astrophysical source. And after that, the electron and the positron detector are releasing the energy in the calorimeter. Here, this calorimeter is made with centiators detectors and the cesium iodine detectors. And then this calorimeter allows to determine the energy, initial energy of the gamma ray photon. So it works in the energy range between 20 MeV up to 300 JeV. And it provides very nice results. You see, there is no collimator. It has a very large field of view, actually 2 steradians. And it's very useful for monitoring the sky and to detect transient events such as a gamma ray burst and novae, for instance. Okay, this instrument is the original goal of this instrument is to study the acceleration of particles in the astrophysical sources. So we know that astrophysical sources are accelerating particles at relativistic energy, and these relativistic particles, when they interact with ambient medium or with the interstellar medium, are producing gamma rays that we can observe in the JeV domain. And this is the goal of the LAT instrument, to study, for instance, the gamma ray emission from active galactic nuclei here, or the gamma ray emission from pulsar. You have the dwarf pulsar that is here. You have also the supernova remnant that accelerates particles at relativistic energy here. You can see this nice image. This nice image has been obtained with 1 year of data. And you can see here, actually, you recognize that this is the Milky Way. And you have, in addition to these sources, so we have pulsar wind nebulae, supernova remnant, you have also here a diffuse emission that is due to the cosmic ray. Actually, these relativistic particles, mainly photons, that are propagating in our galaxy and that are interacting with the gas, mainly proton, hydrogen, to produce the gamma ray emission we see here. Okay, so this is the main goal to study this source. And in addition, also there is some people from the Fermi collaboration that are interested in the dark matter, and they try to find in the galactic center region some signature of dark matter annihilation, for instance, in the gamma ray domain. Okay, so in 2010, Fermi detects a gamma ray from a nova Cygni. The other name is V407 Cyg. And you have here the image that were obtained at that epoch. So you recognize here, you see the Cygnus region here. Oops, it is here. Now it works. Great. It is here. You recognize these 2 sources that are here. We have these sources here, and we have the nova that exploded at that time here. And it was not expected. We did not thought that we did not think that a nova can emit gamma rays at that epoch, and it was a surprise. So we analyze the data. Here you have the light curves that were obtained in the LAT. So you have the flux here in photon per square centimeter per second as a function of time. This is what LAT measures for photon larger than 100 MeV. And in parallel, you have the optical here emission in magnitude. You see in the red and in the green, in the V band, you have the explosion of the nova, and here the decay in optical, and you have also here the X-ray emission that has been detected by Swift. And we detect the third day, we detect here the first emission, and the X-ray emission was low, and then when the gamma ray emission finished, there is an increase in the X-ray emission. So this is interesting because there is a link between the two. And actually, this X-ray emission is the signature of the shock. So a shock here, and this shock can accelerate particles with the Fermi acceleration process. And these accelerated particles are the origin of the gamma ray emission. And so this is what we thought at that epoch. Our assumption was that the ejecta of the white dwarf here is interacting with the wind, the slow wind of the red giant. And in the interaction between the ejecta and the wind, you have the shock that occurs, and the shock accelerates protons or electrons, or the both. We did not have at that epoch. And these high energy particles are producing gamma ray by interacting with the ambient medium. So the principle for producing gamma ray in this JeV range is the following. So you have either protons that are accelerated here and then interact with ambient hydrogen to produce pi0, the neutral pions. And these neutral pions decay quickly into gamma rays. They are produced at high energy, so the gamma rays are Doppler shifted. So it provides not a line, but a broad feature. And this is this broad feature that you can see here, the spectral feature. Here you have the spectral energy distribution that is shown. So you have the energy as a function of time and per square centimeter, per second, sorry, and per centimeter, as a function of the energy. And you have this band, which is in black, characteristic of the pion decay signature. Okay, the other possibility to produce high energy gamma ray is to use high energy electrons still accelerated in shock that may, for instance, interact with the gamma ray from the red giant. So the gamma ray, sorry, not the gamma ray, the infrared photons from the red giant. And in the inverse Compton process, the high energy electron is producing high energy gamma in the Compton process here. And the other solution is that the electron is interacting with an ambient proton, for instance, by the Bremsstrahlung process, and is producing high energy gamma. So this model is also working to explain the gamma ray emission. As you can see, you have in blue what we call the leptonic model. So this is what we call the hadronic model, and this is the leptonic model. The thing that is interesting is that to obtain this pi0 model, we need the best fitting photon spectrum to provide this shape is a photon spectrum with a power law and with a slope of about 2. Negative slope, obviously, but is 2, about 2. This is the best fitting slope, and this corresponds to what we expect in case of Fermi acceleration, or what we also call diffusive acceleration. In shocks, we expect to have this kind of slope. This is not the case for electron, for instance. For electron, the spectral shape of the best fitting electron spectrum is far from this condition. So it means that, okay, we have an idea that the shock, there is a shock, and the Fermi process, the Fermi acceleration process, is at the origin of the emission. So was that gamma ray emission really unexpected from that kind of source. This is what I told you. We did not expect gamma rays from the symbiotic nova. And actually, before the explosion in 2007, Margarita with Vincent Tatishev worked on that analysis, work on the variation of the shock velocity observed in areas of Fuki. This is another symbiotic nova that exploded in 2006. So you can see here the shock velocity observed from this nova in 2006 as a function of time, and we see that the velocity is constant here and then decline. Okay, you see the velocity measured with infrared data, and you have here the velocity obtained with the X-ray data. You can see that in both cases, you have this decline of the velocity. So what the issue is that this decline of the velocity is not expected in case of an adiabatic expansion of the shock here. And so instead, to explain this increase in the rate of decline of the velocity, they suggested, Vincent and Margarita suggested that actually to explain this variation, it means that there is diffusive shock that accelerate protons up to TeV energy. And this is shown here. You have this model that allows to explain this variation. You have this the energy of the proton that is increased as a function of time up to the maximum value due to the spike, actually the zone of the shock where the proton escape, and it explains to the decline of the velocity here. So at that time, obviously, you didn't predict that there would be gamma ray from this kind of event, but obviously, when we have tera electron volt protons, we expect that these protons interact with ambient medium to produce gamma ray. So actually, we cannot say that this gamma ray emission was not expected. Okay, 2 years later, we detected 2 other novae here. So you are here still the map, the image of the 407 Cyg, and here we have 2 novae that were detected in gamma ray with LAT Fermi. But in this case, this is not symbiotic nova like V407 Cyg, but it's classical novae. And in 2013, 2 other novae are detected, and the last one in that period is in 2015, with 2 novae here. For instance, the 2 LAT are very faint, but are still the significance of the detection is enough to claim the detection. Okay, so this is an issue because we thought and we explained the emission with the shock of the ejecta of the nova with here the red giant wing. And in the case of classical novae, here we have the secondary is the main sequence star, so there is no wing, and so there is no the matter for the ejecta to interact with to produce the shock and the acceleration. So it means that there is other process than this invoked for the symbiotic nova. So we study the spectral energy distribution. So you have the spectra of all the sources presented here at that epoch. And actually, all the spectra can be explained with a base-fitting proton spectrum with the slope of about 2. So here again, we have the signature of the Fermi acceleration. But we were honest. We claimed that electronic model using electron via Anderson-Tone or Bremsstrahlung can also explain the shape of the spectral energy distribution. But this this slope of 2 so is the signature of Fermi acceleration, and so we suggested at that epoch that there were internal shock within the nova ejecta that accelerate proton and produce this bump-shaped spectrum. There is one thing to say: the shape seems to be very different, but actually we have a low constraint. We fit with the data this kind of spectrum. This is the proton spectrum. We fit it with the data. So the proton spectrum is the input. We convert that with the pion zero decay process, and then we fit the slope and the cutoff energy of the spectrum, because we expect that the polar spectrum has an exponential cutoff shape. And actually, what we found that we don't have any strong constraint on the maximum energy of the proton. It is the cutoff energy. And you can see here, you have the map showing here the significance as a function of the detection, as a function of the slope, and the significance of the peak, sorry, as a function of the slope and the log of the cutoff energy in GeV. And you see, okay, we have a slope of about 2 roughly here, and sometimes a little bit more here. But concerning the cutoff energy, you can see that in most of the case, we don't have any constraint. So actually, because the sensitivity at high energy of LAT Fermi is not enough, you can see we have only upper limits here. We cannot determine accurately the maximum energy of the gamma rays. Okay, so the question was, do all classical novae emit gamma ray, high energy gamma ray, as detected so far? So what we did is we searched for gamma ray emission from all the novae that were discovered in optical from 2008. This is the launch date of the LAT experiment of the LAT Fermi telescope to 2015. This is the period we studied at that epoch. And actually, what we did is to search for, because thanks to the wide field of view of the LAT instrument, we monitor the sky in 3 hours. In 3 hours, we cover all the sky, so we can detect sources in the sky. And so we search for emission at the position of the nova discovered in optical, and we made a slicing window of 15 days to check if there is excess from these sources. And actually, we found evidence for it's not, we can claim detection, but we have the 2 sigma significance here for 2 novae in the Carina region and in the SCO region here. And you can see here the map that shows the excess. And here you can see that the flux that are detected in this period as a function of time is correlated with the explosion and the observation in optical, as you can see here. But the error bar are quite large, and but there are evidence for emission. And the spectra, we don't have significance enough to provide the best fit of the spectrum obtained by these 2 sources. So we discovered 2 other novae, and we actually we detect these 2 at the 2 sigma level. And for the other, we did not detect. So it means that either there are no gamma ray, so there is no the process of producing by the shock the gamma ray, or the sources are too far to be discovered. Okay, so we performed a preliminary study, population study, and we found that actually gamma ray novae are not standard candidates. So this is a very preliminary population study, because the population study with only, as you can see here, we have only 8 sources. Yes, we have 4. Yeah, there is 8 sources. One is missing here. It's this one, because this one has been discovered in gamma ray before to be discovered in optical. The angular distance between the sun and the nova moon here, monoceros, in 2012 was the 20 degrees. So we did not detect the optical emission. Instead, we detect the gamma ray emission. So we do not know here the peak, the apparent peak magnitude of this nova. That's why we have only here 7 sources. Okay, so we found that the gamma ray novae are not standard conducts. It means that the amount of energy emitted in gamma ray are very different from a nova to another, taking into account the distances. We try to find some correlation between the flux and the peak apparent magnitude. So there is no clear correlation. Here you have the upper limit obtained with the 75 novae. Yeah, the novae. We try to also to find a correlation between the gamma ray flux and the rate of decline of the nova. So the rate of decline is the duration for nova to have a reduction of 2 magnitude in optical luminosity. And so you can see that there is no correlation. Okay, so for the moment, we don't have any helpful information to know more about these sources. Okay, but in 2016, we detected, I didn't work on that nova, but a team led by Lee detected the very bright emission in gamma ray of this nova in the Sagittarius region. And he found a clear correlation between the flux in gamma ray, that are the value here, the cross, you can see here, as a function of time, with the optical. Here you have the optical flux. So this is the magnitude converted in the optical flux. And you can see that you have a clear correlation of the variation in gamma ray and optical. Mainly because you have the decline here, you have the dip here, that shows this correlation. This was at that time, which was the brightest nova detected in gamma ray. And later, in 2018, in the Carina region, there was another very bright nova, brightest than the previous one in gamma ray. And you can check here, we have 10⁻⁹ per second per square centimeter. So the peak is about 1.5. And here we have 10⁻⁻, and the 1.5 is here. So this is slightly brighter. And this one, you have the magnitude in optical, and here you have the flux as a function of time. And you can see a strong variation in optical, and they are clearly correlated with the variation in gamma ray. And this is very interesting because it means that the gamma ray and optical are correlated together. And at that point, it suggests that the shock, because we know that there is shock to produce gamma ray, the energy released in the shock feed or drive the optical luminosity. And this is the shock over a significant fraction of the optical luminosity. And you have here a summary at that epoch of what we detected. So there is the ratio of the luminosity in gamma ray divided by the luminosity of the equivalent black body. So it's an optical luminosity. And you see that we have, as a function of time from the bright gamma ray novae, something quite constant here, but the ratio between the two depends strongly on the nova. For instance, for the 339 Delphi, you have a very low ratio, while for the 3024 scope, you have a large ratio that is close to 1% here. So it means that 1% of the optical luminosity is found in gamma ray, and the average is about 2 10⁻³ here. So it's very interesting, and actually it triggers on the theoretical side some understanding of the phenomenon here, and we have Metzger that investigated this internal shock in the nova, and the model he proposed is explain what we observe. First, that we have the nova that is constituted. Okay, you have an ejecta and a fast wind. So the method I use, the process to explain the gamma ray emission is the interaction of the fast wind here with the slow ejecta that is ejected first, and then you have in this interaction you have a shock that is produced, and you have a forward shock. So actually this is this part here. You have in blue the ejecta, in red you have so the fast wind, and you have in the fast outflow here you have the shock that is constituted of forward shock and a reverse shock here, and in the forward shock and the reverse shock you have the diffuse acceleration of particles here, and you have the acceleration of protons and electrons too, and this accelerated particle interact with the medium here with a cool central shell, for instance, and also produce in the shock you have also a lot of X-rays that are produced, and these X-rays are within the shock are within the ejecta, and so the X-ray release their energy in the slow outflow, and that is at the origin of the optical, or not all, but a large fraction of the optical emission. And it explains why you have the variation that you can see in optical, which is related to the variation with the luminosity of the shock, and so the variation of the luminosity in gamma rays. Okay. Okay, so now another theoretical investigation is the calculation of the particle propagation by solving the equation transport that has been done by Pierre Jean here. So he modeled the system as proposed by Metzger here, and calculates the particle propagation, the acceleration, and the gamma ray emission. And actually, he fits the ejecta and wind parameters with the LAT Fermi data of the 8 novae I presented so far. And we have here an example of the best fit he obtained. And actually, he found that hadrons are mainly at the origin of the emission, and the hadrons are, I mean, the photons are accelerated up to 100 JeV at the reverse shock, actually, here, at the reverse shock. So to explain what we observe in gamma ray. Okay. Okay. Now, going back to the observation, we have this very impressive outburst of arrays of Euclid in 2021, and this is now up to date the brightest nova seen in gamma ray so far. So this you can see here you have the image before and after the eruption, and you can see that the brightness here of the nova is equivalent here to the galactic center region. It's very bright. Okay, the duration is about 1 day for the maximum of the peak. So you have here the flux as a function of time. You have the optical emission as a function of time, and you have here the X-ray emission as a function of time. And you can see here that the emission in gamma ray span up to 40 days, more than 40 days here, and decline as a function of time in the same manner as in optical. And you can see here that the X-rays that are measured by Swift XRT are delayed. The peak is delayed. It's because you have the first emission here in X-rays that are strongly absorbed by the ejecta, by the opacity of the material between the shock and the observer. And after that, the ejector, as the ejector is expanding, the opacity is reduced and the X-ray escapes. When we have a look on the spectra, you can see here the spectra at the maximum period here. We have still this bump-shaped here. That is characteristic of the pion zero decay. And we have a best-fitting model with a slope of 2.3, and we have a lower limit for the energy cutoff. And this bright nova, as this is a symbiotic nova, so here again we have the similitude with the classical novae. We have for this nova here a clear correlation between the gamma ray and the optical, and here you have the correlation that is shown here as a function of time. You have the ratio, which is very nicely constant, with about 2.8 10⁻³ except at the first day when the nova was the brightest, and in the first day the ratio is slightly lower. And when we look more in detail in this first day, we can see that here it's fine, but between in the first day we have a ratio which is very low, and this is due to an attenuation of the gamma ray, but likely due to a lower photon flux. Okay, so I'm skipping that here because I don't have time. And this nova was the first to be detected in the very high energy domain. The very high energy gamma rays is the tera electron volt, TeV, and this nova has been detected with S and magic. So you have here the spectrum, the spectra obtained by S here in two periods. So the explosion was the 8th of August, and you have the spectrum here the 9th of August, and then after we have another spectrum the 13th of August. So in this case, you can see a change in the spectral shape, and this is not seen in the gamma ray in the JeV domain. In the JeV domain, the spectrum is the same, as you can see, the intensity change. But here you have the 9th of August, a spectrum that got at high energy sooner than at the 13th of August, where the slope is here harder. You have here you have this effect is likely due to the effect of acceleration. So the 13th of August, there have been enough time for proton to be accelerated up to. So you have here a maximum in gamma ray at about 1 TeV. It means that the protons are accelerated at about 10 TeV maximum. So this spectral variation is very nice to study the evolution of the shock. And here with magic, you can see that they fit the magic data and the LAT Fermi data that are mixed. Magic is here, LAT Fermi is here, and actually they show, the magic teams show that an hadronic model fits better the data than a leptonic model. So they try to check if electron interaction can produce the shape of the spectrum, and that here you can see that at low energy we don't have this cutoff, and at high energy the slope is not very nice. So we have a constraint here, interesting to see that the proton are the origin of the emission. Okay, there have been several. It's finished. Okay, there have been several modeling efforts here to understand the correlation and the light curve in gamma, high energy and very high energy gamma. So I skip that. And so this is the status of our understanding and the open question. So do all novae emit high energy gamma ray? We can say yes. We don't detect some of them because they are too far. is there a difference between classical and symbiotic novae? It's not obvious because the spectrum, gamma ray spectrum is the same. The ratio of the gamma and optical luminosity is similar, and a model involving internal shock can explain also the emission of symbiotic novae. So we don't need an interaction between the ejecta and the red giant wind. Okay, concerning the acceleration process, we have some discussion here. We discussed already that. For the hadronic electronic origin, okay, we see that the spectral harmony is favored for hadronic origin. And there is, on the theoretical point of view, there is also a problem to accelerate electron up to a tera-electron volt energy because the electron cool quickly via the inverse compton and synchrotron mechanism. Okay, and just to finish, we can fix the constraint or answer to the question if the gamma ray emission is from hadron or lepton, thanks to the detection of neutrinos. So this is a model we have made in 2010. If the proton is at the origin of the emission, so we expect neutrino to be emitted due to the decay of charged ions. And if we detect neutrino from a nova, high energy neutrino from nova, we have here a clear confirmation of the hadronic origin. And the future, from my point of view, but okay, I'm involved in, is the observation of the very high energy gamma ray emission from novae with the Cherenkov telescope array observatory. So I don't have time, so I skip that. You maybe know this. And we already have, it is actually the CTOO observatory at the north hemisphere at La Palma. We have 4 large-sized telescopes and several medium-sized telescopes. And the large-sized telescope already detected the emission of RSOPP in 2021. Okay. The next event we expect is T Coronae Borealis that should erupt, should explode very soon. And we wait for that with all gamma ray instruments. So this is the conclusion here, and sorry for being so late. Thank you. Yeah, you can trigger questions.
Thank you. So I will start with a very nice question. I'm sorry, I'm very far from the field. I expect that for this point acceleration because there is some magnetic field on the surface of this product.
Yeah, actually, there is a initial magnetism that is embedded in the shocks, in the ejecta, for instance, from the start. But you have compression in the shock. And in the compression, you have an enhancement of the magnetic field strength that allows to do the Fermi acceleration. So the Fermi acceleration is possible because the charged particles are confined by the magnetic field.
Yeah, because we have studied the same kind of phenomena around very young stars. So we think that we can observe magnetic acceleration in the press. So what is the kind of magnetic field you have that you expect? Well, to basically reproduce your data. But I think if you have very strong magnetic field already, like we studied, it seems to be a very dominant mechanism, and this is known to increase terms of gamma rays by a lot, and it explains the lack of correlation you have with any of these nova parameters and whatever the time of the scale and everything else. I mean, this is something that the models are predicting that is really in high magnetized dot conditions may increase a lot of these gamma rays. So,
yeah. Actually, for the moment, the intensity of the magnetic field is estimated by assuming equipartition. this is not correct, I agree, but this is a main, on the theoretical side. We have a compression of the gas, we have a high temperature due to the shock, and then with this equipartition assumption, we have magnetic field strength that here are about 0.1 Gauss. And at higher value, but 10 to the 7, something like that, per square centimeter. And this is, and the temperature is 10 to the 4 Kelvin. And we have this kind, for instance, this team fitted here a leptonic model, and here with this leptonic model to explain the radio emission, they need a magnetic field of 0.05 Gauss. This is very low. Yeah, and so just I don't believe this. And Margarita and Vincent estimate also the relation between the radio and the inverse Compton, and they show that if we have such emission in radio, we don't have this inverse Compton. We have an inverse Compton level which is 2 orders of magnitude lower. This is just to explain. So for the moment, the magnetic field strength we estimate in the shock is about 0.1 Gauss or larger than that. This is on theoretical. So I'm more in the observational domain. So I'm not clever with the. This instability will explain the streaming. You are talking about, yeah. This could explain, yeah, 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 yeah. It can explain, for instance, the streaming instabilities can explain the 2.3 slope. For the classical Fermi acceleration, we have something that is about 2. And when you have the streaming instabilities, in addition of that, you have a slope that is deeper, and you obtain something like 2.3, or like here, what we can see, 2.3, 2.4, 2.5. So the streaming instability helps to explain, but I don't bet anything. I'm just observing.
Just a comment from my side that at the beginning you mentioned that the gamma ray emission from novae was not predicted or expected, and I was not directly involved in this, but was the first witness of the work.
Yeah, I remember. We have some exchange.
And Margarita did, and it was predicted. So we were looking for novae because they predicted this. And I remember a paper in 2007 and 8. There was a conference in 2008. Yes.
Yeah, you're absolutely right. And this is something, I'm part of these papers, for instance, Abdo et al. And all the, what we call all the communication associated with that. And we said we did not expect such a source to emit gamma ray and so on. And here, I'm here at IEC just to clarify that it was expected, actually. And I remember, because the work of Vincent and Margarita here, we observed RSOFUK in X-ray at that epoch with the Swift and Jerry Skinner and Auguste Ndiani. And we detect the hard X-ray emission, yeah, and the shock in X-ray with this source. And so this work here is a proof that it was expected. And so this is why I said we claimed at that epoch that it was expected. This was not expected, but actually it was expected.
It was expected. There was even more than something expected.
Are there people involved in the PKO here? You, I know, but other, no?
Well, in our group there are several.
Okay. because my feeling is that the future is CTAO, because with this, we will be able to measure the maximum energy. We don't know the maximum energy of the protons. With the LAT Fermi, we have not the sensitivity enough to have the cut, and with the Cherenkov telescope array, we will be able to detect that. And here, just to show some estimations that have been recently actually it's published this year. And you have here the spectra as we know the energy as a function, and you have also the sensitivity of the large size telescope of at LAPAM. And you can see that we detect only a rest of 50, but for the other novae, the cutoff here, but actually the cutoff is not really known, but okay, it will be hard to detect the other novae, the classical novae, according to this. But we don't know because we don't know the cutoff energy. So we can, CTAO will help on that.
You mentioned these internal shocks for classical novae. So basically, due to the interaction between a low ejecta and a fast wind, which I guess is just like a fast ejecta, right? Fast and slow ejecta. What is the origin of the difference in the ejecta, and if these like, let's say, the condition that determine ejecta different velocity cannot explain why this gamma emission is so variable?
So there are several questions. Yeah, no, but it's normal. The difference between the slow, the ejecta is due to the explosion. Is by the.
Bonjour, je m'appelle Siri. Elle fut saisie, détruite.
Sorry. She cannot help to answer. Sorry. So the slow ejecta is due to the nuclear explosion here, and so it's powered by the nuclear decay, and okay, and the burning of the hydrogen in the on the top of the white dwarf is still hot. I mean, make the white dwarf hot, and here with the radiation pressure, you have a fast wind because the ejecta has already pushed a little bit the material around, but you have this fast wind that occur. But actually, the velocity between the slow ejecta and the fast wind are not so different. Actually, sometimes it's about 1,000 of kilometers per second. We use, for instance, maybe a little bit more for the fast wind for this. But maybe Margarita can answer better than me concerning the difference in velocity between the two. And your second question was?
Maybe since you mentioned that there is no, for example, relation between the gamma ray luminosity, the filter and the distance between different novae. Maybe let's say the conditions when you create this gradient in velocity between shells can be very variable. So that explains why this novae can be very different gamma ray emitted.
Yeah. This is a good point. There is the ejecta mass also, because to produce gamma ray, you need, if you don't have target, proton target, you cannot produce pion zero, neutral pions. So you need also the mass. So it is a mess. And no, this is a degenerate problem. And this is what, for instance, Pierre Martin found. There are a lot of solutions for each source. So now what we need is thinner, little less broad error bars and ideally very high energy values to have a fit, a better fit and a better constraint on this parameter. That's why I think that high energy and very high energy observation will help a lot to understand the ejection mechanism in novae, and not only in symbiotic but also in the classical novae.
Just a short question. the parameters of the systems where this emission has been measured are known. For instance, the mass of the white dwarf, the mass of the nature of the companion is well known. Right?
And this is not taken into account, for instance, in the modeling. For the model, we just have the mass of the ejecta, the velocity, initial and the final velocity. Actually, we have a kind of bubble flow, and so we have the wind rate. I mean the mass per year produced by the wind with the velocity of the wind, and we have the delay between the start of the wind and the ejection, the ejecta. This is all the parameters, and obviously we fit the fraction of the matter that is accelerated in the shock. So the fraction of protons that are accelerated in the shock. And so so it's completely independent of the mass of the white dwarf and the separation with the secondary stars and so on. And that's why I think one of the efforts that has to be undertaken in the future is a population study. Because now we have up to now 25 novae detecting gamma ray. And so it's a lot of effort to, we have to find all the information for each of them, try to find the mass, for instance, of the white dwarf and so on, and try to find correlation between the gamma ray emission and the property of the nova. And we know that massive nova will produce higher velocity ejection here, and then with a lower mass. So we expect that there is a correlation between the mass and the gamma ray emission. That it has to be undertaken in this case. This is something. Yeah.
But if you have no correlation, probably doesn't come from my physics.
Yeah, it's something. If we don't find, for instance, correlation with something like velocity and so on, we have to fine tuning then our understanding in the microphysics. It's true.
This model of blue shocks in classical knowledge has not been developed in detail.
Yeah. This is rough.
So,
yeah, it's
yeah.
For
the not like the other figure on the internet, but also because the observations.
Yeah. It's
many observations for this nova is a very good opportunity for the classical knowledge. Not so.
Yeah, there are not enough accurate measurements for classical novae. We see a very nice in the symbiotic, for instance. We have Carina in 2020, 2018 was bright. We see a lot of structure in that. It was a classical nova. But okay, it's clear that this model has been developed. I mean, this theory has been developed by Metzger in 2015. Okay, now 10 years ago, that he didn't made a lot of other detailed simulation. Unfortunately, Pierre Martin stopped to work on that topic, and this is a pity because it would be great to improve the spectral wave, improve the transport equations, the secondary stuff, and so on, and to estimate, for instance, the radio emission. There could be a very interesting constraint in the radio observation.
This is also
yeah.
So many observations of all emitting ranges, and in this case,
yeah.
These are the models to improve a lot in the interpretation of the observation for the observations of all energy ranges with all the instruments. But for all your novae, it's not the case. Sometimes. Thank you again.
Thank you for the invitation. I'm sorry for the improvisation.
It's really not. Also, it's